Tell you what, open notes, open book, and I'll fill in the answers for you.
Let's do it.
Why not?
Oh, no.
That's it. I just pass out tests already filled in, and all you have to do is write your name on them.
So Professor, the exam will be the same as this, right?
Yeah,
Exactly that?
exactly. I don't know about exactly, but it'll be close.
How many percent close?
2.
Wow. Don't ask those questions.
Don't ask. Guarantee that it's going to be black ink on white paper. All right. There's no burning questions. This is a rather strange idea. We've got 100 keV photon. Let's see, you're thinking 100 keV. You're thinking, what was the tube? So what was it? The voltage setting for the tube? X-ray tube. Things like that. You're thinking about the wavelength of this thing. All the things come to mind when you see a photon that has some energy, right? But none of which we're particularly interested in right now. And that photon is going to hit that aluminum plate, 1 millimeter of aluminum. And the photon is going to go right through it. And the question is, what is the energy of that photon when it gets through the other side? How much energy does that photon have when it emerges from that 1 millimeter aluminum plate? Well, let's keep it simple. More, less, or the same?
Less energy. Less energy goes through the aluminum.
So the photon passes through the aluminum. When it comes out, does it have more, less, or the same, or have no idea?
Less energy.
Okay, everybody's at least fairly uniform on that, so we can correct it all at once. It has the same.
How?
I don't even do that.
It didn't do a thing to it.
Oh, because it has so much,
What?
such a high KV.
Oh, the KVP doesn't change?
That's the weird thing about it. Yes, the KV doesn't, the energy doesn't change.
Oh, okay.
So what is that aluminum doing? It's just sort of in the way, but invisible.
It filters out weaker energy photons.
There you go. So let's have some weaker energy photons.
Is that what it means? I'm sorry.
Let's have a 90, 80, 70 keV photons. Only thing that emerges are the 90 keV and the 100 keV photons. What happened to the other two? Our 80 and 70 keV photons. They went in and they got absorbed. So 4 photons go in, 2 photons come out. There was some absorption occurred. Yeah? All right. You know how to calculate an average of something? Calculate the average energy going in and the average energy coming out. How do you calculate an average? You add up the 4 things, divide by 4. On the other side, you add up 2 things, divide by 2.
So we calculate the average energy of the.
Calculate the average energy in and calculate the average energy out.
Okay.
And see what you see.
55.
95 coming out.
85. 75.
Can I use your calculator? Actually, you know what, I got it.
47 point. Oh, where's the chapter?
All right, what happened to our average energy?
It went up.
That's what filtration does. It increases the average energy. It's kind of a strange idea. How does it increase the average energy?
By removing the lower end.
Yes, get rid of those poor performers and you can increase the average. Yeah. It's the whole idea of filtration. So X-rays can be removed from the beam either by scattering, which case they go off in a different direction, or by absorption. So there's two ways you can reduce the number of photons in your beam. The beam that remains is said to be attenuated. Word here. So attenuation is just a reduction of the beam intensity by scattering and absorption. Just pointing out that that's another special word that has a special use and meaning that often comes up just as something you kind of need to recognize when you do see it. All right. So now the game is, we have some X-ray beam. With some initial intensity. And then we have some filter. So we have initial intensity of the beam and we have the intensity after the beam. What can you say about the intensity after the beam?
Stronger.
You will have a lower average. Lower average number. I mean, a higher one.
Higher average energy,
Lower intensity.
but there's fewer photons in the beam, less intensity. So the lower intensity but higher average energy. So then they give you something like this. They make a table of thickness. What's he calling it? He is calling it X-ray quantity. And he's measuring this in milliroentgens. So it's a measure of X-ray quantity. And without any filtration at all, this is, by the way, on page 141. This is 1.18, 2, 6.3. 0.29. So as you can see, the game here is that the more thickness, the more aluminum, the more millimeters of aluminum that you put in front of the beam, your X-ray quantity goes down. And now the really challenging game. Approximately what thickness of aluminum would reduce the number of photons by half?
Yeah.
3 millimeters.
If you start off with 1.18, what's half of 1.18? 0.59, and what's close to 0.59?
Two.
Somewhere between 2 and 3. So 2 is probably as close as you're going to get to it. So this is known as the half value layer. And the more aluminum that you need for your half value layer, the more penetrating your beam is said to be. The larger the half value layer, the more penetrating the beam is said to be. Pretty straightforward idea, huh? It has just some sort of interesting little implications here.
The lower the half value.
Yeah. Often abbreviated as just HVL for half value layer. All right, let's see if we can play another game here. start off with some beam. And we have some filtering here. And we have a beam that emerges from that. Okay. And I'm trying to figure out what comes out of the second filter. Two filters. The first one happens to be at the half value layer, 2 millimeters. And the beam that comes out of here compared to this beam. Compare those two beams in terms of penetrating power.
Twice as much?
Not really twice as much, although I got some of the idea. This beam, we know, has fewer low energy photons.
So be more penetrating than the.
So it's going to be more penetrating than this beam because it's been filtered. Okay, if this beam is more penetrating than that beam, if I want to reduce it to half again, what can we say about the half value layer necessary for that beam?
Could be higher than the first one.
Bullseye, you got it. All right. The second half value layer. Is greater than 2 millimeters. Because the second beam is more penetrating than the first beam. Another word used to describe this process is hardening of the beam. Kind of a strange idea. The beam is harder, it will penetrate more is kind of the linguistic direction that you're going in there. So just to summarize this chapter, it's all about factors that affect X-ray quality. How does MAS, changing the MAS, affect the X-ray quality?
Like increase amount of X-ray photons.
Sorry, I didn't write this quite correctly. Quality and quantity. What does changing the MAS do?
The contrast increases.
So you're thinking of a graph.
It affects the number of photons.
It affects the number of photons. What kind of graph are you thinking about? Of two different MAS curves. You have that graph in mind?
Like the second MAS curve would be a bit larger area than the first one.
Any other changes?
Higher average.
What? Two curves, one has twice the MAS than the other one, but all other factors are the same. How would you draw that?
One small hill and one bigger hill. That's
Smaller and bigger, okay. So your answer to this question, what changes?
Quantity.
Quantity.
Quantity only, quality does not change. No change in quality, quantity changes with MAS. Okay, what about KVP? You increase the KVP, what happens? Quality increases. Definitely on the quality. And the quantity. And what about distance?
Could you increase one more voltage extra electrons depending upon it?
It's the quality.
Quality or quantity? What changes with distance?
Quality.
Quality.
And probably
You're
quantity.
farther away, if you increase the distance,
Quality
That's quantity
changes.
and quality.
why? The quality changes.
And I think the quantity, not all.
How does the quality change if you increase the distance?
The energy level decreases.
The energy level decreases.
You'll need a higher energy to make up for the increase in distance.
We'll need a higher energy to make up for the increase in distance.
Quality
Reduces
decreases.
the intensity.
Yeah, distance just reduces the intensity of the beam, but it doesn't change it.
So quality, no.
So you'd have the same distribution of, if all you did was change the distance, you'd have the same distribution of photons. Same energy distribution of photons, you just have less of them. I don't think we had a graph for that. Let's make one. Interesting idea. What is a graph that would illustrate the change of distance? If you had your some kind of X-ray detector twice the distance, what do you think it would look like? No, good idea. No, darn. Good idea. I like this graph. Okay, here's curve A. Put a little characteristic peak there, just to remind ourselves about characteristics. And B is twice as far. So we've doubled the distance, say from 30 to 60 centimeters. So the distance for A is 30 centimeters, and the distance for B is 60 centimeters. And that's all we changed, we just changed the distance. And what can we argue?
The quantity drops.
The quantity's gonna drop. Do we know how to calculate that drop? What's that change in intensity?
D1 square
Do you have a name for it? Process?
inverse square.
Inverse square law. So if we double the distance, the intensity decreases by 4. So the intensity of B is going to be 1/4 the intensity of A. And the only thing that's going to change is just the height of the peak, not anything else in the shape. So we would like to have a curve that has 1/4 the area. How would you draw a curve that has 1/4 of that area? Yeah. Something that looks like that. All right. So distance changes the quantity.
The average be the same.
The average would be the same. No change in quality. All the features would be the same, just just less of them. And one last factor, filtration.
Reduce efficiency, increase? Okay.
Yes, your quantity reduces if you increase your distance. And what does filtration do for quantity and quality? Increase?
Quality and decrease quantity.
Decrease. Yeah. So this is table 8-2 on page 142. Those are your important factors. And you should have some idea of graphs that would represent those changes. Things to get out of your graphs that you're going to have on your page of notes, right? You will have those graphs. All right, we're done with this stuff now. We're on to chapter 9. So before we leave this, do you have any leftover questions for the exam on Monday? Yeah, it's in chapter 8, so it could be there. And it's completely related to it.
No, I'm doing the outline. I'm just gonna relax. That's why I did the early factors were. Yeah, I don't have a particular.
Okay, we have to get into chapter 9. Yeah, that's the last chapter. This is, to me, it's this a more fun chapter. We're done, more or less. Yeah, we're doing good. We can always go back and hit a few other things, but okay. So, before we launch into chapter 9, as you notice, it's all about X-ray interactions. So it's assuming that you've already produced the X-rays. And just one more time, how are the X-rays produced?
X-rays are produced by the X-ray tube, when electrons strike the target.
When electrons stuck to target. All right. Yeah, just have some verbalization of how are X-rays produced. Oh, high energy electrons strike a target. So you could word that X-rays are a result of electron interactions with matter. And the reason I wanted to emphasize this is because Chapter 9, we are sort of going to shift gears and have a different point of view. Up to now, we've mostly been focused on the electrons hitting the target. Chapter 9, okay, the electrons have hit the target. We don't care about them anymore. We are now fully into just concerning ourselves with the X-rays. So we're putting aside the electrons. And now we're just going to focus on the X-rays. All right. So, most important. Something called the photoelectric effect. This is the topic for which Einstein got his Nobel Prize, for explaining the photoelectric effect. What does it sound like, photoelectric?
Like the light.
Photon in. Think of it this way, photon in, electron out, photoelectric effect. It's kind of the opposite of what we do with the electron and the target. In the target, we hit the target with the electron and a photon comes out, kind of. In this case, photon is going to hit something and an electron is going to pop out. So it's kind of the opposite. So we need our old friend the atom and its shells. K shell, L shell, M shell. We have some electrons floating around here. We have the nucleus. All of that's looking reasonably familiar. Okay. So what kind of, we're going to have a photon come in and do something. And what kind of photons do we normally use? If we're thinking about photons, and particularly in the range of energies that we might be using, what kind of photon energy might we expect? 100 keV photon, 70 keV photon, 50 keV photon. Let's take something around the middle. Let's say about, say a 70 keV photon. And that's, now you need to step back and think about the binding energies of those electrons, because we're going to knock one of those electrons out. And which of the electrons are the most tightly bound?
Okay.
K shell, yes. So what's going to happen is the photon is going to be absorbed and it's going to knock out the K shell electron. And let's just say that this K shell electron binding energy round numbers, we'll just say that the K-shell binding energy is 68 keV. And so you're saying, well, there's more than enough energy for that photon to knock out the electron of that K-shell, right? That seems pretty clear. But energy has to be accounted for. So if I have too much energy, where is the rest of it going?
Gets absorbed by the atom.
Or absorbed.
Going into heat, but we want to be a little more clear with that in the interaction. It is ultimately going into heat, this is true. So we're going to go in, knock out this K-shell, and it takes how much energy to knock out the K-shell electron?
68.
That's the incident
68.
photon. I was pointing it to see if you would just follow the finger or the words, and it worked. You followed the finger. It takes 68 keV to knock out the K-shell electron. We have 70 keV. We have 2 keV extra. That keV, that 2 keV goes into the electron energy. So we understand the process. Energetic photon knocks out a K-shell electron, and there's some kinetic energy given to the electron. So now we need to put it into symbols.
Just 1 second, when you say these 2 keV goes into the electron,
Kinetic energy.
for the whole atom, or is
No.
it a specific shell?
See, our K-shell electron, our photon is going to come in, and it's going to knock this one out, and it's going to cause that electron to go screaming off in that direction.
Oh, the same electron that's.
Yeah, the electron that was in the shell goes screaming off in that direction. And so now it has kinetic energy. So some kind of symbolic representation. What are we talking about? Energy conservation? Yes? Yeah. Energy in equals energy out? Yeah? Okay. Can you write that down? We're going to try to see if I can get you to turn it into symbols. Energy in equals energy out. And what is our energy going in?
70. Okay.
It's the 70, well, let's be a little more broad. It's the energy of the photon. So why don't we have that be something like EP incident? EP, the incident photon, some symbol that will lead you to think of the incident photon energy. And then, what happens to that incident photon? It's absorbed. And in the process, we have to spend its energy with the binding energy of the electron. So some symbol to represent the binding energy. Like EB. Just want to see if I can get you to write it down before I write it down. And then what else do we have besides the binding energy of the electron? The kinetic energy of the electron. Suggestive symbol might be EK, yes. So hopefully what you have looks something like this. The incident photon is equal to the binding energy of the electron plus the kinetic energy of the electron. Seems so easy now, doesn't it? Yeah, that's all there is to it. For our considerations, the photoelectric effect primarily interacts with K-shell electrons. It does happen with the outer shell electrons, but we're mostly interested with this interacting with the K-shell electrons. So what do you know about the binding energy in K-shell?
That's the binding energy is the highest in K-shell.
Yeah, it's the most tightly bound is in the K-shell. That make sense to everyone? All right. And where is this atom that our photon ran into? It's our poor patient. Yeah, this is not the target anymore. This is the patient. We're hitting the patient now. We're bruising them. We're knocking their electrons out of their K-shells. What kind of atoms are we going to run into in the body?
Carbon.
Atom.
Mostly carbon, yes. What other kind of?
Hydrogen.
Hydrogen, lots of hydrogen.
Oxygen.
Oxygen, and so there's a whole bunch of different types of atoms. So what we need to know is, how does the K-shell binding energy depend on the atom?
Larger atoms have a higher binding energy.
Exactly. So the question is, how does the K-shell binding energy depend on atom size? The larger the atom, the more binding energy it has. I'm using PE for photoelectric effect. So the probability of a photoelectric interaction increases with the atom size. What also increases with the atom size? You have a bigger atom, what do you have more of? Electrons and protons and binding energy. So we're going to write this down as, we're talking now the probability of a photoelectric interaction. So a probability of a photoelectric interaction is proportional to Z cubed. meaning that the higher the Z of the atom that we're hitting, whether it's calcium, oxygen, there's some iron atoms in the body as well, right? Any other heavier elements in the body? Any gold?
Iron,
Iron, where do you find iron in the body?
bones.
Blood.
Blood.
Bones, yeah, there's iron pretty much everywhere. How about some gold?
No, you're not supposed to have gold.
Not supposed to have gold? I got a few crowns.
That's why we
Yeah, I know, we're not
ask,
supposed to.
you know, especially
Yeah.
gold crown.
Yeah, gold crowns, yes.
Anyway, they don't x-ray them out, I guess.
Go to
Or
the
they
dentist
might, they
office.
might, but-
Yeah, so because of the binding energy, we're thinking photoelectric effect, inner shell atoms, and because those inner shell atoms are so tightly bound, the probability of getting some electron with a binding energy that's approximately at the photon energy goes up with the bigger the atom. So that's why it's proportional to Z cubed. Oh, and which structures on your X-ray radiographs appear the whitest structures that you see?
That's, that's.
So the white areas are a result of this part of this probability here.
Oh, calcium.
Yeah, things like bones, whatnot, the heavier, the more of them, the heavier effects. So remember that all the white areas is because we have absorbed that photon. And what else happened when we absorbed that photon?
Happens to what, the patient's body or the picture?
To the patient in the picture. Yeah, let's talk about the patient. Because what is this process of absorbing a photon?
Attenuation.
It is attenuation, but you don't want to tell the patient they're being used as an attenuator. We're just going to use you as an attenuator here. Same idea, but where is this little creature going?
It's gonna hit their cells.
We've ionized the atom. Their, one atom of their bone has been ionized by this photon. And what is this thing going to do now? It's headed off someplace else to the atom next door, to which it causes possibly some kind of radiation damage. You've now got an electron screaming over to the atom next door and, say, breaking up the DNA molecules. So we got the good effect of absorbing that photon. We got the bad effect of knocking out an electron, which is going to go off and do some other damage. So that's why it's not all good. But put up with the bad in order to get the good benefits. So the electron that goes screaming off because of the photoelectric effect can cause some damage. All right. Other things about photoelectric probability. So the photoelectric probability is also proportional to the density of the material. If you make something more dense, it's more likely to absorb. So the more dense the material, the more likely it is to absorb a photon. So we have to get over this idea of density. What is density?
How thick an object?
Density is how thick an object? No. It's mass over volume, yes. So you're thinking of something like a pound of lead and a pound of feathers. as a prototype example of density. Which has more mass, pound of lead or a pound of feathers?
Same.
They have the same mass. Which has more volume?
Same. Wait.
Pound of
No.
lead and a pound of feathers.
The lead.
Which has more volume?
Lead.
Feathers.
The feathers have more volume.
Feathers.
But the, yeah,
So what is the density of the feathers compared to the density of lead? Much less, yes. Because you're putting a really big denominator on the bottom, right? That's why. Okay. So we need something, you don't want to have too many competing effects here. Something that has two different densities but is actually the same stuff. Sounds rather exotic. It is rather exotic. But it's very, very common.
Both are metal, but they have different densities.
They have different densities, but it's the same stuff. Does it sound like anything you might have heard of? Water and ice, yeah. So it's the same stuff. So if we have water and ice, here's a couple of ice cubes. And this is water. Of course, this is like looking at a top view of this cup of water with some ice cubes floating in it. And if we wanted to, have the image receptor here and our X-ray machine coming down like so, what's going to happen to the X-rays as they interact with the water and the ice?
They get more absorption that way? It's not necessarily nice.
Does the ice absorb the same way the water does?
No.
The ice is less dense. So did I tell you how it goes with density? I did say the more dense it is, the more likely it is to absorb. So what is the most likely to absorb, the water or the ice?
Water.
Ice floats.
The water. Oh.
Ice is less dense than water,
yeah.
right? Okay, so the ice is actually less likely to absorb than the water. Okay. So if you can imagine what's going to be the light and dark regions on this thing.
All dark, all light, 2 dark spots,
All light and 2 dark spots.
or spots,
Why 2 dark spots?
because they're less dense, and so it's kind of like fat and tissue, like it's less dense than bone. So I would assume the water would be more like bone, it would be white,
Beautiful. Yeah,
and then it'd
great.
be more gray.
Nails it.
Got one.
So if we were trying to kind of do something like this, we would expect to see some dark spots because there's less absorption, followed by some lighter spots, which I don't have any way to draw, but you got the idea. That was an excellent description, thank you very much. Yeah, so that's just like a good example of what this density effect is. All right. We need Z effective. And we have 3 entities. We have, 4 entities there. We've got fat, soft tissue, lung, and bone. Lung, yes, this is table 9.3. page 152. Okay, and well, let's start off with fat. The periodic table doesn't contain fat. So what is fat probably made up of?
Water.
Water, carbon, and things like that. And so the effective atomic number is 6.3, kind of if you average all of the stuff together. Soft tissue, 7.4. Lung, 7.4. These are just effective atomic numbers. Bone, 13.8. So bone is made up of heavier stuff than what the lungs are made up of. And lung and soft tissue have, and fat are all pretty lightweight, low atomic number stuff. And then there's another table, density tables. He has the same idea for effective densities. But if you put them in different tables for whatever reason, so this is 9-5. They put them together here at one spot. 320, 110, 1,000, 1850. And these are all in SI units of density. Kilogram per meter cubed. And so now you can see huge differences between, say, soft tissue and lungs. Well, maybe not huge difference. Definitely between fat and bone, there's a big difference.
You mixed up the fat and soft tissue and there's
Oh, we switched the orders. How silly of them. Good catch. Soft tissue is 1,000. That is 910. And the lungs, there we go, 320. That's making a lot of sense. Lungs being mostly air. Very low density, those lung things. Bone, very high density. And you're trying to think about probability to absorb. So, higher density, more likely to absorb. Higher Z, more likely to absorb. So, which is going to be the most likely thing to absorb a photon?
Bone.
Bone, yeah, it's high density, it's got high Z value. And the least likely to absorb?
Lung.
Lung. And this is probably your experience, right? This is what you've been seeing. The lungs are pretty, not much there, and the bones there. Okay. So let's compare the, we want to compare a couple of probabilities. So our photoelectric probability is proportional to Z cubed, and it's proportional to density. And so now we want to cook up something like case A. Okay, the answer is going to be pretty obvious, but case A, we have a 70 keV photon in fat and a 70 keV photon in bone. Which one is more likely to be absorbed? The bone. Okay, so that was the easy part. How much more likely? So the notation here is a little abstract. We're trying to write the probability of photoelectric absorption. That's the capital P with the subscript, photoelectric in case B, probability of photoelectric effect in case A. I would like to get rid of some of those subscripts, but we're going to have a few other things to deal with, so I need to keep the subscripts around. All right, so this goes easily enough. This goes as the density in B times the ZB cubed divided by the density of A. This, I'm using the symbol rho for density. This is a Greek character rho. I'm not sure what he uses for density symbols. Yeah, that's what I'm going to use. So now it's easy to calculate. We just have to look up, or we already have them up there, we just have to get the appropriate numbers. We said the density of bone is 1850, and the density of fat was 910. And we have the effective atomic numbers 6.3 and 13.8. And we calculate away. And I come up with 21.4. Are we calculating that?
No units?
No units. No units.
Nine.
Isn't that nice? No units, but we need to put this into a sentence.
Oh.
Go back to the original question. What's up there? How much more likely is case B than case A? You did a calculation, now go back and write the sentence. Exactly. Case B is 21.4 times more likely than case A. And of course, that's what makes the whole X-ray concept so useful, that the bone is such a much better absorber. Where do you have trouble distinguishing features in the X-rays? Which elements are the hardest to work with? I mean, I don't know how you guys are taking the pictures, not me. But,
Organs.
don't you have to worry about organs and whatnot?
Yeah.
And they're hard to image because
Can't
They
see
almost
them.
have the same dense.
almost have the same density, almost have the same Z. Probability of absorption is nearly the same. So that's the effect. So what do? Contrast, yeah. How does that work?
Drink it or eat sunshine.
Okay, that's how you get it in the body. I got that. Now that you got it inside the body. What I meant is, how does it work in this process?
That the contrast is more density than the rest of the body.
More density and probably a higher Z. So you're getting more absorption that way, and you're getting them to show up. All right. One more process here.
So currently the contrast is heavier, so what happens
More absorption, more likely to absorb.
when it goes into your organ?
Yeah, what do they give you? What do they use for contrast agents? Darian, that's what I was thinking. I couldn't remember the name of it.
You can drink brandy, but not inject.
You drink it, not inject it, right? Okay, probability of photoelectric absorption. This is one more relationship for our photoelectric absorption. It's inversely proportional to the cube of the energy.
And that's the energy of the,
Photon, EP.
and the PE is photon electric. Right?
The PE is photoelectric, and the capital P is probability of photoelectric effect is proportional to the 1 over the energy of the photon cube. So what is that telling you? Not telling you anything? It's an inverse relationship, yes. As you increase the photon energy, and you complete the sentence,
Probability.
it's
increase.
less likely to be absorbed. So as you increase the photon energy, it is much less likely to be absorbed. That cube is a pretty strong effect. Okay, we've got our old friends, the 70 keV photon and the 70 and 100 keV photon. Which one is more likely to be absorbed?
70.
The 70. That was the easy part. How much more? What are you going to do? I haven't told you how to calculate it, but I think you know how to calculate it. It's an inverse relationship to the cubes, so you have to have the cubes in the opposite, the energies in the opposite order. So this is 2.92. And then we put it into a sentence. 70 keV photon. Three times more likely, just about. So is that your experience? Higher the kVp, what happens to the image as you raise the kVp, changing nothing else? What happens to your pictures? You don't know yet?
No. I know it has, doesn't the object have to be like thicker?
Well, suppose you just do the same object and you just do it with the higher and higher energy. What do you think might happen?
Less contrast.
Less contrast. Yeah, you're just punching the photons right through the object, you're gonna get less contrast.
They don't really like us to do experiments like that.
I know. Oh, well. But you can imagine, it's sort of a thought experiment. Just lay there still while I try something. All right, we'll stop there. Have a good weekend.
Because it's coming on Monday.